Okay, here it is. This is our test review. We're doing heat and heat transfer, kinetic, potential, thermal energy, properties of matter. The two quizzes that you've taken, we'll review that. So let's go right away. Right here, we're going to do kinetic and potential energy first. We did this the first day of school. Again, the kinetic energy is movement, right? So we're moving. Anything that moves, we have kinetic energy. That's the movement there, right? Let's use another color for the kinetic. Why not? Let's use that one. Why not? And this is stored. This is the energy that's stored in an object, right? So that's the difference right there. It's a very easy difference. Mass and movement, mass and position, which I'll go over. So let's just clear that out. And again, when we're doing these videos, if you don't understand something, just rewind the video. There it is. So here's an example, right? We have someone holding a ball, right? Hopefully it's not a brick. So here we have, get our page marker back there. What color should we use today? Who's going to guess, right? We'll use blue, right? Who guessed that? So here's this person, and there is the ball or whatever it is, and that's the potential energy, right? It's the energy that's stored. And when she lets it go, that's the kinetic energy, right? The movement is the kinetic energy. So when she lets it go, there's 100% potential energy right now in there, 100%. And as she lets it go, halfway down, it'll be 50-50. And then when it lands, and hopefully no one's hanging out over there, when it lands, it'll be zero potential energy, but then it'll have 100% kinetic energy. So that's one way to look at it. And most students don't have a problem with kinetic and potential energy. We've done these experiments in class. So here's a person that was using this principle, Galileo Galilei. Here he is, right here, just hanging out in jail, perhaps. We talked about how he went to jail. But by the way, Galileo was born. He was born the same year as someone you should know, right? Here he is. Here's Shakespeare. They were born the same year. Of course, Shakespeare with Romeo and Juliet and Hamlet and Othello and all those other plays that you'll read about or have read already. So Galileo, he was proving that a Greek philosopher, Aristotle, was wrong on many things. And Aristotle lived many, many years ago before Christ. So what he did is he proved that two objects with potential energy, the same potential energy, doesn't matter how heavy the objects were, they would land at the same time on the ground. So yeah, there's Shakespeare again. How you doing? All right. And also, here's Michelangelo's famous sculpture. Michelangelo actually died the year that Galileo was born. Just to give you a reference, right? And there's Aristotle. Well, here's the experiment. So at Pisa, which is in Italy, and here's the Leaning Tower of Pisa. It doesn't really lean this way. Let's go get my page marker back up there. Right? But he threw these two different objects right here, and it didn't matter what they weighed, they landed at the same time on the ground. But Aristotle, who lived in 322 BC, before Christ, right? Aristotle said that two objects will fall relative to their mass. And we know Galileo said this was wrong. They will not. And later in the year, we're going to talk about why it actually works, because there's something called inertia that we'll talk about later. All right, let's clear that out. Let's close it out. Move this down. All right, and by the way, in the Apollo 15 astronauts, David Scott, he did this experiment on the moon. He dropped a hammer and a feather. And since there's no air on the moon, they both landed at the same time. So David Scott proved that Aristotle was wrong also. And there's Aristotle, because there's no pictures of him. He lived 322 BC, a long, long time ago, before Jesus was born. And so there's a little marble statue of him. Now, there's a lot of things Aristotle did right. He was a great philosopher, and he really helped with metaphysics and logic, but that's in a different lesson. We'll talk about that. So one thing also that Galileo proved that Aristotle was wrong in is the heliocentric and geocentric principles. Now, helio means sun, and we believe this today. We believe in this principle. We believe that the earth goes around the sun. But back in Aristotle's time, they believed the earth was the center, not only of our solar system, but the earth was the center of the universe. And then there was a person named Copernicus who lived before Galileo, and Copernicus said, he was doing the math, and the math said just wasn't coming out right. So Copernicus came up with the heliocentric. So again, helio is sun, geo means earth. This was the view a long, long time ago. They believed this. And of course, they didn't know much planets beyond Mars. That came about later. Galileo actually knew about Jupiter, and he discovered the moons of Jupiter. One, Ganymede, we talked about in class, is the largest moon. You should remember that. All right, let's close that up. So again, this is just the geocentric. Earth in the center is not correct. This is the center now. And again, this is not the center of the universe, because at Galileo's time and Copernicus's time, they didn't think the universe was anything bigger than our solar system. So remember, we live in a giant universe, and in our universe, we have billions of galaxies, and you should know our galaxy. Our galaxy is the Milky Way. And of course, there's other galaxies like Andromeda we'll talk about later in the video. So again, this is a Copernicus, say that 3 times. Copernicus came up with this theory, but it wasn't published. When he did, it was published after his death, and then Galileo proved it right, and he went to jail for it. So imagine that, going to jail for some scientific proof. All right, going back to potential energy and kinetic energy, just so we have it down. Potential energy is mass and position. Kinetic is mass and speed, or mass and movement. All right, so let's pause this for 1 second. All right, and here's another example right here. Let's get this out of the way. Bring our marker back. What color am I going to use now, right? Who can guess again? Why don't we use orange? Why not? Oh, this color, whatever that color is. Mustard. No, orange, actually. So again, when you have a pulley and you're lifting up the pulley, you're lifting it up, and right here, all this potential energy is stored, ready to drop. Gravity is going to drop it. And then when you cut the string, as you see right here, there's the kinetic energy, right? We've done examples in class with a bow and arrow. When you pull back the bow, that's potential. Let it go, that's kinetic. And we also done it with a roller coaster, right? On a roller coaster, you're going up the roller coaster wherever you are, Six Flags, Adventureland. So at the top, you have all this potential energy, right? All this potential energy. You let it go about halfway. Again, remember we said it's 50-50. And then at the bottom, you have, now it's all kinetic energy. Potential energy is very low. The kinetic energy is going to carry this up. It's like momentum carrying it up, and it's going to continue until it finally just slows down, and right there. So if you want to pause the tape, this is right there as I cut right through it. All right, let's clear that out. By the way, just a little more tidbits on Galileo. Isaac Newton, who we're going to talk about a lot in science because of Newtonian physics, the one who gave us calculus, he was born a year after Galileo died. And Copernicus, by the way, lived before Galileo. Not too earlier, but for example, if you want to get a perspective on Copernicus, Columbus, Christopher Columbus, Cristoforo Colombo, he lived. He was born about 20 years before Copernicus. So just to give you a frame of reference. All right, let's do. And here's what you should know about energy: the ability to do work. That's energy. Let's go on to our next topic: heat energy, thermal energy. So again, what happened there, right? Let's fix that 1 second. All right. So we have here thermal energy, right? Thermal energy is just the sum. The sum. If you add up the kinetic and the potential energy, you get the sum of all the particles. That is heat energy or thermal energy. It's also called internal energy. So let's just write that down there. And we want to use red. Let's use green. Why not? It's also called internal energy. Right. So the sum of all the kinetic and potential energy is thermal energy. And all heat is the flow of thermal energy. That's all it is. And we've showed pictures in class. Right, we've done the experiment where we put dye in hot water. We can see how the flow of energy is happening. So again, heat is the flow of thermal energy. When you put hot, and you shouldn't do this, right? But if you put hot tea on your hand, the heat's going to flow to your hand. And if you put an ice cube on your hand, the heat from your hand is going to flow to the ice cube, because heat will always flow from warmer to cooler objects. And it's going to create this equilibrium. An equilibrium is just a balance. There's a balance happening, trying to get the same temperature. That's what temperature does. And we'll talk about that in a minute too. So again, thermal energy is the potential and kinetic energy added up together. And you get this thermal or internal energy. Some people call it heat energy. But the heat itself is the flow of that. Okay, so thermodynamics is the study of this. And if you go into college and go to engineering or go into more about studying heat, it's thermodynamics. And you can see cold, the heat is flowing to the cold. And then if you touch something, we've done this in class also, if you touch a piece of metal, metal is a great conductor of heat. So when you touch metal, it feels colder. You can have a piece of wood and a piece of metal in a room, and they're going to be the same temperature, but one's going to feel cooler because when you touch the piece of metal, right, the heat from your hand, let's get the page marker up here again. The heat from your hand is transferring to the metal faster. And again, some metals will do it better. Like, for example, silver or copper. They'll do it better than that. And where is our page marker? There we go. And again, let's use yellow. See how that works. Now, whatever that color is. So again, here's this piece of copper, let's say. And when you put your hand on it, the heat is going to flow out of your hand. It's going to we should have used red. Why don't we use red? Right, so here's the heat for red, right? So it's going onto the copper because it's conducting better. But on the piece of wood, it doesn't conduct that well, so less heat is coming out of your hand, right? And so you don't feel that cold. So again, they're the same temperature, but metal conducts better. And the best conductor, as we said, who remembers the best conductor? The best conductor is silver. That is the best conductor, followed by copper and aluminum or aluminum. The metals themselves are better conductors of heat and of electricity. So we've done this. We've talked about this early on the first day of class. Who has more thermal energy? Well, the iceberg. Let's get that out of here. We don't want that, actually. The iceberg has a lot of thermal energy, only because it's so massive. If you take this coffee cup, you couldn't even see it in the picture, right? So let's just say if I put a little dot there, that wouldn't be the coffee cup. Right? You wouldn't, from this picture, if I put a coffee cup on this iceberg, you wouldn't see it. So we know that because it's more massive, this iceberg is gigantic. It dwarfs this, right? So it has so much. We'll just put all these particles. It has so many particles, but they're scattered about. They're moving very slowly. In fact, because they're in ice, they could be all together connected, but they're vibrating. They're not moving like in the coffee cup. In the coffee cup, they're moving. They're incredible. They're moving so fast. And remember, the faster particles move, the hotter it gets. So the coffee cup is hotter. It has a higher temperature, but it doesn't have more thermal energy. The heat is flowing faster. But again, more thermal energy in the iceberg, but the coffee cup has a higher temperature. So that's one thing we have to look at is temperature. Temperature is just the average kinetic energy of the moving particles. So in the coffee cup, it has a higher average kinetic energy because they're moving faster. But it doesn't have more thermal energy. So keep that in mind. Again, the faster things move, the hotter it gets. We did first day of class, we did this experiment, right? We all rubbed our hands and we felt that heat. And again, the faster we moved our hands, with the more pressure we used, we can get hotter. Our hands will get hotter, right? And then we can measure temperature. And you know this, we in the United States we use Fahrenheit, but the rest of the world uses Celsius. I mean, there's only a few countries, the United States, Bahamas, Liberia, in Africa, they use Fahrenheit. But the rest of the world uses Celsius, and in science we use Celsius. We also use Kelvin. Especially scientists use Kelvin. So water will freeze at 32 degrees Fahrenheit. That's something we know. If it's salt water will freeze lower. We talked about that also. Or 0 degrees Celsius, right? And Kelvin, you just add 273 to Celsius. Add 273 to Celsius, and you'll get whatever Kelvin is, right? So 0 degrees, just add 273, and you have the Kelvin. Always add 273 to Celsius. Add that to Celsius right here, and you'll get whatever it is in Kelvin. All right. So if you see here, we have absolute zero. Absolute zero is the coldest something could be, theoretically. We don't know if we can go colder than that. We cannot create absolute zero in the lab. We can't get it that far. But in theory, if everything stops, if all the particles stopped, you would get absolute zero. And it's 0 Kelvin. And it's negative 273 Celsius. So if you just added 273 if you add 273 from here, you get water freezes at 0 or 273 Kelvin. Just add 273. It's the same thing. So water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. And this is the other chart here. We have to get used to the fact that, and it's much easier when we use Celsius. 0 and 100 is much easier if we're looking at from Fahrenheit. So we're going to have Fahrenheit, and we have to convert that so we can get to Celsius. And then with Kelvin, we just add 273. So try to remember that. So again, absolute zero is in theory. Here's just a better look in a chart. You can see water boils at 212 degrees Fahrenheit or 100 degrees Celsius. And here's a chart you can just look at. So again, we're using Kelvin in science. We're using Celsius in science. And if we have Fahrenheit, we have to convert it. Okay. And here's some of the temperatures on the planets. Last quiz, I assumed you knew certain sizes of the planets. We'll go over that again. So Jupiter is the largest planet. It's actually much larger than Saturn, even though from this picture it looks like Saturn's rings go beyond Jupiter, but they don't, because you can fit every single planet in Jupiter. You can fit 1,000 Jupiters in the sun, just to tell you how gigantic our sun is. But then again, our sun is small compared to a lot of other solar suns out there. So Pluto, as you can see, look at this temperature here. It gets cold on Pluto, but it doesn't reach absolute zero. And on Earth, we're not going to get anywhere past this mark, right? So this is the Fahrenheit, and here's Celsius. So in Earth, you could probably, you may get these temperatures around here in Antarctica, but you're not going to get anywhere near this on Earth. So those are just the temperatures. All right, so if we look at the formula, here's the formula for converting Celsius into Fahrenheit. We've done this in class, and let's do it again. So let's say you have, let's say Celsius. Use page marker again. Why don't we use something different? I don't know. What about this one right here? What does that look like? That looks nice. So let's say Celsius was 0, right? At 0 degrees. We already know that Fahrenheit will be 32. You're just plugging in the C, just plugging in 0, right? So it's 1.8 times 0 is 0. And adding 32, and Fahrenheit will be 32. So that's all we have to do that, right? We're just plugging in. Remember, anytime you see a constant, there's here 1.8, this constant. This is a coefficient. You should know that name. The coefficient is the number, and it's next to a letter. This is multiplication. So let's do another one here. Pause the tape and try this one. What if I said Celsius was, let's say, 20 degrees? Celsius was 20 degrees. Pause the tape. What do you think Fahrenheit would be? All right. So, again, plugging it in. Just plug in the 20 to the C. So 1.8 times 20. That gives you 68, right? And 38. That is 38. Gives you 38. And just add 32 to it, and you get 68 degrees Fahrenheit, right? So 1.8 times 20 is 36. Well, wait a minute, let's do this over. 36. So again, 1.8 times 20, let's make sure we do that. That's 36, right? And then we just add 32 to that, and we get 68 degrees Fahrenheit. Always double check to work. It's easy to make our happy accidents. Oops, made a happy accident. Again, always double check. Don't rush and don't submit so quickly. All right, that's part one, and we'll talk about the rest of what is on the test in the next one. Great job today, people. Smile.